Hello everyone, my name is Purak Jain and I will be presenting a paper on SERP interference network and its applications in search marketing. I represent the search and social marketing science team at Amazon. We are responsible for getting traffic from off Amazon websites like search engines and social networking apps to Amazon. The way I've structured the presentation today is that first I'm going to talk about why we are interested in SERP pages and then introduce our motivation with an application within search marketing, which is related to experiment design. And then quickly talk about how you can replicate some of our work and deploy this at scale. So let's dive right in. SERP stands for Search Engine Results Pages. This is how a typical search engine result page might look like. We see different type of results here. The top two boxes are paid or sponsored results. The first ad format is what is typically called a shopping ad. The second one is the more traditional text ad. The bottom two results are organic results, which again could be in different formats. In this screenshot, you see organic results with product images. These are called free product listings. And the last one is, again, the more traditional organic search result. Now, what do we mean by SERP interference network? So, as an advertiser on search engine, you might see the presence of your e-commerce website listings across all of these formats, as you can see here for Amazon. Now, if you imagine each of these results as nodes in a graph with an edge between them, if they show up for the same search query, for example, Reebok shoes here, that's the interference network we are going to talk about today. At the offset, if we can build something like this graph has a lot of potential applications. We will talk about one of them in the presentation today. So let's talk about shopping ads carousel. Let me give you a quick overview of how advertising on a search engine would typically work. The search engine, which is the ad publisher in this scenario, holds an auction. A lot of advertisers, Amazon being one of them, put a bid for our products. If our bid is competitive and if our ad is relevant to the customer search query, the search engine might show our ad in the shopping ad carousel. Users may or may not click on it. If they do click, then we pay the search engine for that click. Our team builds these real-time bidding algorithms for Amazon's shopping ads program. Whenever we come up with a new bidding algorithm, we need a way to A/B test it. Since it's off Amazon, we cannot split on Amazon customers. So we try to randomize on geolocations, but for shopping ads, a lot of the key search engines like Google or Bing, they don't support geo-level different bids. So we end up randomizing on products. We have a group of control products and a group of treatment products. The challenge with that is that since the search engine controls which products are relevant to which search query, it might happen that a product from the control group and a product from the treatment group go into the same auction. That violates the stable unit treatment value assumption, or SUTVA. So at the end of the experiment, the lift we are measuring from the treatment is not only because of the treatment, but also because of the between product spillover effects. Now, a common technique to counter that is designing cluster randomized control trials. So to get around this, what we do is we started looking at some of the performance reports that ad publishers, aka search engines in this case, provide advertisers from some of the programs. One of that is a search query report, which provides us for products where we got an impression. Search engine tells us what's the actual search query that the customer searched for. So if we look at a sufficiently longer time period, say around 2 years back, we can build a large-scale bipartite graph to see for which search query on the search engine, which of our products got an impression. And then we can use that data to try to model the interference at the experiment design phase itself. One thing to note here is that we are using the ad publisher's data. We could potentially build a search query to product bipartite graph using Amazon's own internal search data. But what we learned is that the notion of interference we are trying to build the network for is very different on the search engine side, because they not only look at the relevance of the product to the search query, but also the bid competitiveness. So the kind of products that a search engine shows for a search query could be very different than what Amazon shows on its side for the same search query. Also note that the edge weight between these nodes is the number of times that product showed up for that search query on the search engine for a given time period. So once we have this bipartite graph, and since we don't control for which search queries a product is shown, we take a weighted one-mode projection to build a unipartite product graph. To do so, we need a projection function to project the scores from the bipartite edge weights to this unipartite graph edge weights. We also need this projection function to not be computationally expensive, since the graph size could be in the magnitude of around 400 to 500 million nodes. So intuitively, what we're trying to do is that if two products have high probability to show up for the same search query on the search engine, then we make those two products have an edge with a higher weight between them. One additional thing we did, we added this later on, was downweighting the edge weight by the log of the frequency of search queries. This is because we have certain upper funnel search queries, for example, buy gifts, which can show up for any product in our entire catalog, right? So that leads to a lot of connectedness in the one mode projections. So we downweigh the contributions from those search queries. Now, once we have the unipartite graph, we need to create product clusters. So what we're trying to do is, instead of randomizing on products, we're trying to randomize on these product clusters, and we're hoping that the interference is contained within those clusters. To do this, we need to balance between two objectives. One is we want to maximize the number of clusters as they translate to randomization units. So more the randomization units, more the power of the experiment. But we also want to minimize the between cluster edge weight. What we do is look at this leakage, which is essentially the percentage of edge weight which is across clusters upon the total edge weight in the graph. And if we measure this leakage across different values of the number of clusters, and we look for an elbow point where we can have the optimal amount of clusters, which do both minimize the between cluster edge weight and also maximize the number of product clusters, we take that optimal point. We tried a few different network dismantling algorithms. The one we ended up using is called METIS. In addition to balancing these two objectives, one good property about METIS is that it also ensures that each of the clusters have around equal number of products. So it won't happen that you have a cluster which is like 2 or 3 products and then a cluster which has like 1,000 products. Yeah, so once we create these clusters, then we use these clusters to randomize between control and treatment groups. We can balance on different metrics like the traffic volume, the revenue, and profit. So we have a stratified randomization. One thing to note is that the leakage metric in the previous slide kind of overstates the spillover, because at the end of the day, we are just interested in minimizing the spillover between the control and the treatment arm. For our A/B test, we ended up creating 10,000 clusters, still a 36% leakage, as that was the elbow point in our leakage versus number of clusters plots. We saw a huge difference in lift estimate for the same treatment, the same bidding algorithm, when we do a simple product randomization, which was around 44% lift, versus when we did a product cluster randomization, which was around 24% lift. The 24% lift is in line with what we actually observed on dialing up the treatment 100%. So this gives us a lot of confidence in minimizing the risk from spillover using the methodology we described. So how do we practically do this for 400 million plus node graphs, right? For our example, in our case, when we look back at around 2 years of data, we were talking about a graph of size 6 to 7 terabytes. So we needed a Spark-based distributed backend to run the ETLs. On the other hand, the graph partitioning library, aka METIS, is a highly optimized C-based library. And then we do the experiment lift analysis in R. So each step requires a different language and a different compute. We use AWS SageMaker pipelines, which allowed us to do such polyglot programming. This ensures stickiness between what we prototype, what we A/B test, and what actually goes into production. This blueprint of the system architecture will allow us, anyone, to implement each of the components of the experimental framework we described today. For next steps, we are looking at a few things. Our current interference network is built using censored data. That is, we only get the data if we win the auction. We are investigating data from platforms like SEO Clarity to get better visibility in the SERP interference network. We are also further investigating the stability of these clusters over time. And finally, with the recent LLM-based search results, we have more unique positions where we can show up, and we want to include these in the SERP interference network. Thank you for listening into our presentation today.